Today's topic is more or less humidity and moisture in thermal analysis and how to achieve that and how to operate with that and under that conditions. I just want to introduce myself. For those who do not know me from some of our past webinars, my name is Sebastian Seibt. I'm head of laboratory here in our Linzais headquarters in Germany. I'm a chemist and I'm mainly working in the lab at Linzais since 2013. I speak German and the English language, and I'm responsible, as said, for requests regarding service and test measurements. A short overview about our company. The Linzais Thermal Analysis, or in German, Linzais Messgeräte, was founded in the 1950s in Selb in Bavaria, in the mid of Germany, where we are still located, by Dr. Maximilian Linzais, who was working on the first dilatometer series for the porcelain industries. That's, by the way, also the reason why we are located here in an area where the porcelain industry was a strong industry in the 1950s, 1960s. We manufacture in Selb. All of our instruments are manufactured here, and we have facilities in the US, in China, and also newest in India, where we do service, where we do measurements, where we do maintenance, and where we do also sales, of course. And besides these 4 locations where we are located by ourselves, we are represented by various distributors all around the world. So in almost every country, there is a distributor for Linzais available you can get in touch with if you have interest in our products or if you want to know more about the one or the other technique or whatever you want. Our company is still family owned. So meanwhile, we are in the 3rd generation. Mr. Max Linzais, or Dr. Max Linzais, who founded the company, passed away in the 1990s, and his son, Mr. Klaus Linzais, took over. And meanwhile, his 2 sons, Florian and Vincent Linzais, are in charge of the company. They are our 2 CEOs. Klaus is already more or less retired. So we are in 3rd generation family owned. We have around 100 employees all around the world. And we have, as said, around 65 distributors working with contracts all over the world in the countries we are not represented by ourselves. Our main business area is the measurement instrument manufacturing. So we do a lot of instruments for thermal analysis. We do thermal conductivity and thermoelectric instruments, and that's our main business area. Besides that, we also offer contract measurements or project research with some project partners here in our main facilities in Germany. And on the pictures down here, on the left picture, you see a data logger, which was one of our very first products, because at the 1950s, when we were founded, we were not producing only instruments for thermal analysis, but also recording loggers for recording the data, because computers were not that common in that time. And on the right picture, you see one of our labs here in our headquarters. Our product range, I just mentioned, covers the so-called classic thermal analysis, which is what I would group the instruments in the upper line, which means we basically manufacture differential calorimeters, so DSC instruments. We manufacture various thermobalances, simultaneous thermal analyzers, which is the combination, the classic combination of DSC and TGA, so calorimetry and thermogravimetry. We have a broad range of dilatometers for inductive high-speed dilatometers for steel industries, optical, classic push rod, and we have thermomechanical analysis for measuring Young's modulus and bending experiments and so on. So that's what we would consider the classical thermal analysis. Besides that, we also do thermal conductivity in many ways. So laser flash technique, heat flow meters, hot wire techniques, which is a very growing field and very big field. We have instruments for thermoelectric properties like Hall effect determination, Seebeck coefficient determination, resistivity, conductivity measurements under temperature influence. The same stuff all for thin films and microchips, coatings and so on. That's what we also do. And besides that, we do a lot of customization. That means instruments that can be equipped with several added coupling techniques like mass spectrometers, infrared spectrometers, Raman spectrometers, maybe high pressure, maybe high temperature variations of our instruments. That's what we also do quite a lot. For all the instruments in the upper line that are highlighted a little bit, which I said would be the more or less classical thermal analysis, so DSC, TGA, dilatometers, we also offer the possibility to couple them or combine them with a humidity generator or with also a steam generator. And this is today's topic. I want to explain a little bit what's the difference between water vapor experiments and humidity experiments, because for many applications like coal gasification, biomass investigations, sorption, stuff like that, water vapor or humidity are needed. And you need to know that there is a difference between just speaking about humidity or real water vapor. On the one hand, you have the relative humidity. The relative humidity is more or less the amount of liquid water that is contained in an atmosphere. That means in our ambient atmosphere, we have a certain humidity dissolved as little tiny water drops in the air. It's not boiled water. It's, if you would consider it like this, it's liquid water drops that are carried by the gas. And humidity can only exist, of course, at temperatures below the boiling point of water. If you want to operate in humidity, you need to stay below the boiling point, you need a carrier gas, and the concentration of humidity depends very much on temperature. For this, we have humidity generators like the big box you see on the picture on the left side. And in contrast, you have water vapor. You speak about water vapor if the water evaporates in its gaseous phase. So if it undergoes the phase change when it's usually boiling at 100 degrees. And from then on, you speak about water vapor. It's the gaseous aggregate state, it's above the boiling point, and it can be used as pure atmosphere. Water vapor is what you get if you heat the water above 100 centigrades, and you can use it directly as a gas, because it is a gas. You do not need a carrier gas and so on for water vapor. I want to make clear that this is the difference, and that's what this talk today is a little bit focusing on, because it's a lot of misunderstanding and misleading in the requests we have and in the instrument configurations we have. So I want to focus a little bit on the difference. But back to the topic, the focus is also a little bit more on humidity, on the so-called relative humidity generator. And I have to explain that the typical range for humidity, as said, is up to the boiling point of water. So usually we speak about humidity from room temperature or ambient temperature up to 80 centigrades. Maybe a little bit lower than room temperature, but of course not below the freezing point. So somewhere around 0 degrees, more or less 5 centigrades is the limit. What you need to know is, as I already mentioned, the relative humidity determines the amount of water in air. So it's more or less gram per kilogram. So gram of water per kilogram air or gram per liter air, whatever you want. And the maximum level of humidity is very much dependent on the temperature of the carrying gas. That means cold gas, cold air, or cold atmosphere can carry lower amounts of total water or total dissolved water in the gas than warmer gas can do. That means if you speak about 100% humidity, which is the maximum capacity a gas can handle at a given temperature, 100% humidity at maybe 10 degrees means a significantly lower amount of water than 100% humidity at higher temperatures. Or in this picture on the right side, you see if you have a certain amount of water, which should not be water vapor, but just water vapor is a misleading word here, sorry for that. So if you have a given amount of water that's dissolved in an atmosphere, it may be 100% humidity at 10 degrees because it's the maximum capacity. However, if you heat it up and the amount of water remains the same, it's only 50% at maybe 20 degrees and only 30% at around 30 centigrades, because the capacity that the gas can carry increases by temperature, and the amount of water can be controlled by a humidity generator or by the instrument. So this percentage of humidity must be calculated carefully at every given temperature, taking into account what kind of gas mixture or gas you are considering. So you need a dynamic control, and that's why we have a humidity generator that can calculate this and can create the humidity level you program or you want. The drawback of this effect and of this physical behavior is that if you have a hot atmosphere with a given amount of water and you cool it down, it's possible that the water that's dissolved in the atmosphere exceeds the amount, the capacity that the atmosphere can carry. So during cooling, you must be sure that there's no condensation or no no water gathering taking place, and you do not flood your instrument. So when setting a humidity into an experiment and you cool down, you have to be careful that you flood it with dry gas to get rid of the water before you cool it. Otherwise, your instrument will be flooded. So that's just about humidity in general. Regarding the capacity I just mentioned, the curves you see is the water, or the maximum water concentration or humidity concentration versus temperature. So the blue curve is the 100% humidity of air versus the temperature. So the amount of water which represents 100% humidity significantly increases by temperature. You see around ambient temperature, it goes down to 0. Of course, on a negative temperature range, there is no humidity given. And by increasing temperature, the amount drastically increases. 20% humidity level is reached, more or less at very, very small concentrations around freezing point, and increases by temperature a little bit lower. And the higher humidity content increases faster, which means the higher you go in temperature, the more water can be dissolved in the gas. That's what you need to know. And at temperatures below 0 or around 0, humidity is no longer existing. We do not speak about relative humidity at negative centigrades, and we also do not speak about humidity above the boiling point. That's just some principles that I just wanted to explain. Before we go into experiments, I also have to mention that there is a certain zone of temperature and relative humidity that's comfortable to animals and human beings. This so-called comfort zone is this green and yellow dot. So the yellow dot is the very comfortable, the green one is the still comfortable zone. So we need a relative humidity between 15 up to 90%, and we need ambient temperatures between 15 and 25 centigrades to feel really comfortable. And this is the range where human life takes usually place, and where all our climate control and our ambient and our living takes place. And this is also the range where pharmaceuticals, where foods and so on have to be stable and have to be used. So if you investigate foods, pharmaceuticals, or stuff like that, life science at all, we are mostly speaking about that so-called comfortable zone. That's the life condition that you have to test and you have to use for your testings if you just want to measure if for instance, if a drug is stable, if a food is stable, if it reacts somehow. You do not only need the temperature range, of course, room temperature, but you also need a room humidity level usually to really represent what happens to stuff in this real life condition. That's what you also need to know. To solve these issues and to make it possible to run our instruments under that conditions, as said, we can equip our instruments with the so-called humidity generators. I already introduced this as this gray box, more or less. And what it does is quite simple. I'm sorry that this is a little bit, on the slide it looks a little bit better, but I'm not sure if you can read that. Basically, you have a dry gas that goes through a filter. Then there's a pressure reducer and a pressure sensor and a flow meter, so you can set the flow rate and the pressure of your dry gas that comes into the system. Then within the box, the dry gas is split into 2 channels. On one channel, there is a water evaporator that's fed by the one split, and the other split goes around it. Using the split valves 1 and 2, the ratio between water carrying flow and non-water carrying flow can be controlled. The flow that goes through the evaporator is always maximum saturated. And then these 2 gas lines are mixed up again. There is a dew point analyzer to make sure that you are staying with the mixture in a below the dew point. And then it goes through a heated transfer line into your thermal analysis instrument. Doing this, the system can easily control the exact level of humidity by controlling the mix up between dry carrier gas and 100% humid carrier gas. The dew point analyzer confirms that it's really the humidity level that you want to achieve, and then it's fed through the instrument. That's what this box automatically does. and it's controlled by software. So in the software, you just enter the level of humidity you want to have, and this controls the level of humidity of the gas that is fed into your instrument. Of course, if that's the only gas you need, the humidity level is exactly the one that you set. If you mix it up with other gases in the instrument, of course, the humidity level is lowered. But that's how we control it, and that's what the humidity generator does. The equipment is quite easy. As said, it's just attached to the gas inlet. Usually there's a heated transfer line that has the same temperature like the carrier gas, that there is no temperature change between the setup in the box until it's fed into the instrument. That's important, that's very crucial. If you would feed it through a cold line, it would immediately, if you set a high humidity level at elevated temperature, you go through a cold line, it would immediately form drops and the water content will be lowered. Therefore, you have to make sure that the carrier gas gets a certain temperature and remains at the temperature until it's reaching the instrument. And this is how we usually do that. Regarding the specs, our humidity generator provides a flow rate of 500 standard milliliters. So standard square centimeters are, or standard cubic centimeters are standard milliliters. So from 500 up to 15,000 standard milliliter per minute. It provides a humidity range of 2% up to 98% relative humidity in the range from room temperature up to 80 centigrades. It can operate higher temperatures, so it can go up to 95 centigrades. However, up to 95 centigrades, you will not reach 100% humidity or 98% humidity anymore. So in the range between 80 centigrades and 100 centigrades, you will reach humidity levels around 90%. That's the restriction that you have to know. The tolerance that we reach is plus minus 1% relative humidity. And we also have a sensor included that also measures with a tolerance of plus minus 1% relative humidity. So it's quite accurate. And yeah, it's a quite accurate and easy way to provide a decent humidity level to your instrument. Coming to the application or coming to the measurement, in general with humidity, there are two possible experiments that could be done. One would be a so-called temperature sweep. So you set a defined humidity level and then you heat your chamber. The amount of humidity or water that you feed stays constant. So the relative humidity in your chamber will change by increasing or decreasing temperature. So you feed with a constant amount of humidity, you swipe the temperature, so the humidity percentage in the chamber will change. We call it temperature sweep. Doing this, you can simulate increasing, decreasing humidity levels by temperature. The other application would be isothermal experiment, where you heat a sample to a certain temperature, stay isothermal all the time, and then you vary the humidity by feeding in a humidity level or pumping in the water until a saturated level is reached, and then you can lower it and vary it by controlling humidity directly. Both ways lead to a very similar experiment. So you change the humidity level and look or watch the influence of humidity on your sample. The typical temperature sweep level is a little bit more difficult to achieve properly. If you want to keep the level constant, the humidity level constant by increasing temperature, you have to increase the amount of water you pump into a system in the same level you increase the temperature, which can be controlled by software, but is difficult to handle. The isothermal experiment is quite easy. It's easier to handle, and the isothermal condition is more or less used for stability studies or sorption studies or water content uptake and sorption desorption experiments. So that's the two ways we usually do. Then I have some application examples. That was a study that a customer did. They were investigating brick samples. They had brick samples at different temperatures. It was basically were different wall brick materials, different quality and different batches. And what they did is they investigated the relative expansion. So it was a dilatometer coupling. They looked at the relative expansion coefficient and the influence of humidity at different temperatures on the relative expansion. On the left side, you see the moisture content versus relative humidity. So the sample or the brick sample was seeing relative humidity levels at different temperatures. So 20 degrees and 60 degrees, it was two batches. So the blue one and the red one were two different samples. They both saw 20 degrees and 60 degrees. and at each temperature, the humidity was increased. After the experiment, the moisture of the material itself was determined by thermogravimetry. So just it was placed on the balance and it was looked how much moisture came off. So as you can see, the moisture uptake was quite slow up to a certain level of humidity. And then suddenly, no matter if it's hot or cold, no matter of 20 or 60 degrees, suddenly the moisture uptake of the bricks increased. And on the other experiment, on the right side, the humidity level was increased and the coefficient of thermal expansion was measured multiple times. And you see, by increasing relative humidity, the coefficient of thermal expansion suddenly decreased from quite significant values to significantly lower values. So at higher temperature, the effect was a little bit shifted, but similar. At lower temperatures, it was also the same effect. You see that the expansion of the sample was heavily influenced by the humidity level. So this is what one customer did with the experiment or with the equipment he got. So he used the thermobalance and he used the dilatometer to get, on the one hand, the moisture uptake, on the other hand, the expansion under influence of humidity. What we did by ourselves was a DSC experiment where we measured the melting, more or less crystallization and melting of food under various humidity levels. And what you see here was the melting and crystallization behavior of a sugar sample. So we tested the melting and we tested the crystallization by DSC. So you see it easily as a peak. So this peak here is the melt. And on the other hand, you see phase transition down here at negative temperature range. And so this is more or less the glass transition. This above here is melting and crystallization. And what we saw is by increasing level of humidity, the melting point drastically was shifted to lower temperatures. And also by increasing levels of humidity, the glass transition was also shifted to lower temperatures. So high humidity level, first, of course, high humidity level, then freezing the sample, and then again, heating it up led to a shift of the glass transition down to more negative temperatures from -44 to -68 centigrades. And the melting point with higher humidity levels, even if it's only 3 or 4%, already shifted the melting from 60 degrees to around 30 degrees. Of course, sugar is a substance that takes up humidity in very high amounts. So if the air gets humid or if you pump in humidity in the experiment, sugar usually tends to form agglomerations and bind the water quite properly. So therefore, it's a very easy and significant effect that you can display here. We are showing this because we have a lot of customers who really investigate food, water uptake or humidity uptake of foods or pharmaceuticals, and then what's the influence on the melting, what's the influence on the decomposition, what's the influence on the way it works or the mode of action and so on, which is quite useful and quite frequently asked. However, most of these customers are not willing or allowing to show their data. So therefore, that's what I'm showing experiments that we can do in our lab easily without harming any interest of our customers. Another example that I can show that we did by ourselves for another customer who was interested in the system was more or less the moisture-dependent diffusion into a polymer sample. That experiment was done on a TGA PT1000 system that was used to monitor mass changes at different temperatures and humidity levels. The same material was used here multiple times between 20 degrees and 85 degrees at increasing humidity levels. So these steps you can see on the curve, these mass change steps, result of we were heating, keeping it stable, isothermal, heating to the next step, keeping it stable, heating to the next step, keeping it stable, and so on. And at each step, at each heating step, of course, there is a reaction. So you need a little while until the system gets stable. Then you heat up again, the system gets stable, you heat up again, the system gets stable, and so on. However, what you see is, as the same sample was used at different temperatures. And these curves are corrected, by the way. So there's a zero correction done without any humidity, and then without any sample at different humidity levels to make sure that this effect that you see is coming from the sample and not by your setup and system. What you see is that the mass increase of the sample at lower temperatures, that the mass increase of lower humidity levels is drastically lower than higher humidity levels. So at higher humidity level, the polymer takes up much more weight, so it takes up much more of the humidity from the atmosphere. This is a test we did by ourselves. We tried to redo what our customers were doing. They can also do that under different pressure levels. And doing this proves that polymers take up humidity out of the air. And depending on if it's high density, low density, what's the surface structure, this influence is dependent on the humidity level, and it's also dependent on the temperature level. And doing this helps manufacturers of polymer parts to make sure to get an idea how fast these polymers age, how fast they lose their structure, how fast they get more or less brittle or can break, and how stable they are, more or less. And this is quite important because polymers are in our daily life almost everywhere nowadays. As I mentioned at the very beginning, in contrast to humidity, and I want to show you this as well, in contrast to humidity, we also have vapor generators for water vapor experiments. Because if you exceed the 100 centigrades at ambient pressure, or if you exceed the boiling temperature of water, because at higher pressures it may be a little bit higher than 100 centigrades, you're in a range where there is no longer humidity. You cannot speak about relative humidity in a range where water is gaseous. In that case, you speak about water vapor concentrations and no longer about humidity. So water is existing as a steam there and no longer as liquid water. So therefore, we speak about steam concentrations and no longer about humidity concentrations. In that case, a humidity generator won't work. In that case, we provide so-called water vapor generators, which is more or less a similar setup. It's a gas control that has an evaporator unit where liquid water is controlled by HPLC pump to control the amount of water that is directly evaporated and then used as water gas and brought into the reaction chamber as gas directly. The picture down here shows the phase diagram, pressure versus temperature. And you see there's a blue line, and everything that's below the blue line is gaseous water. At a certain temperature and pressure segment, there's liquid water, and there's the solid zone, of course. So if you're at low temperature, water is usually solid. If the pressure is really, really low, it's still gaseous. However, at ambient pressure, which is more or less in the range over here, usually water is solid below 0 degrees. At 0, it's melting. You get into the liquid phase. And at 100 centigrade, you get into the gaseous phase. And now the pressure on the y-axis shifts that a little bit. So high pressure means more liquid until higher temperatures. Low pressure means you reach the gas state earlier. And that's why you have to make sure, if you want to use a humidity generator, stay in this liquid zone. If you want to use a vapor generator, stay in the gas zone with the temperature and pressure settings. As I just said, our vapor generator works quite similar than the humidity generator. The only difference is you do not have a carrier gas. You have a gas box for gases that directly feed different gases into the system. So you have a purge gas inlet that goes into the system. You have sample gases that go into a system. However, the sample gases are mixed up or can be mixed up with the gas that comes off the vapor generator. So the vapor generator itself is placed down here. You have liquid water controlled by a HPLC pump, goes to an evaporator where it's boiled, and then you have a mass flow controller for the gas, for the water gas that feeds it into the chamber. You can mix it up with sample gases or carrier gases or additional gases, but it's not necessary to mix it up with other gases. You can use it directly as a gas, as an atmosphere. However, if you use water vapor, the transfer line is always heated higher than 100 centigrades. It's around 200 or 300 centigrades even. You bring in the hot gas directly as water gas, and you also have a heated outlet. So you go into an outlet in the condensation trap after the experiment, and you can also still couple mass spectrometers, FTIR, whatever, but also by heated transfer line in this case. That's what we do regarding the vapor. Also some specs. The flow rate of our humidity generator goes from 10 standard cubic centimeters per minute up to 500 pure steam. So it's a little bit lower rates than for the humidity. We can run water vapor concentrations of 1 up to 100% water vapor in the system for temperature range between 100 centigrades, of course, up to 1600. Our tolerance where we control is very similar with the humidity. It's plus minus 1% of water vapor. The difference is we do not have humidity sensors in here. We just have the water vapor in there. We control it by the HPLC pump that feeds the liquid water in the evaporator, and that's how we know and how our software knows how much water is in there. I have also some applications for water vapor, for typical vapor applications. In general, they are used for thermal balances, DSCs, and dilatometers as well. Many of these applications involve high pressure instruments. So they are mainly, real steam generators are used for high pressure SDAs, high pressure TGAs, either in the floor mounted big reactors or in the tabletop high pressure systems. The main application we did a lot of times, and we are always asked for if we speak about steam, is coal gasification or biomass gasification, where you heat a carbon containing sample in a water containing atmosphere to get a so-called gasification reaction. This graph on the right side shows what happens. This is one of our reactions. So you have biomass or coal gas or coal sample. The red curve shows the mass of the sample over time, over the experiment. So you see there is a decrease and there is a sudden big decrease of mass. The green curve is the pressure, so it's an isobaric experiment at 50 bars. The purple curve is just the purge gas flow. There was a purge gas as additional gas involved. And the blue curve shows the water vapor concentration. So what was done here was the sample was heated up to a certain temperature. During heating, there was a little mass loss, which is the volatile components, like solvents or hydrocarbons that just burn off or evaporate at lower temperatures. And that's what you lose anyways. And once you reach the target temperature, we switched from just purge gas to water steam. So we activated the steam generator around 80 minutes, somewhere here. And once water steam reached the sample, the so-called gasification reaction started. So the bound carbon reacted with water to form carbon monoxide and hydrogen. This reaction even goes on and forms methane in the very end. If you keep on feeding water, you end up having methanol and methane out of the carbon, and the sample mass decreases drastically. So all the coal and all the accessible carbon of your sample usually is consumed. This reaction usually forms or is used to form methane, methanol, and other hydrocarbons and accessible gases that can be used for further reactions for chemical industries and so on. And it's a way to determine how much accessible coal you have in rock samples, in brick samples, in charcoal, brown coal, whatever you bring. Varying the temperature and pressure also gives you an idea about composition of your sample and the accessibility of energy and bioavailable carbon. We had customers who are doing this with plant-based from soy plantings or from wheat and other plantings, and they always try to get rid of the waste that they produce. It's bio waste, and you can use the bio waste to just burn it off, of course, to generate heat, but you can also use it to access the bound carbon to get worthy products like methane, methanol, other gases, other hydrocarbons that can be used for chemical industries instead of just burning them off. As said, that's the main application for steam in contrast to our humidity generators. That's what I wanted to show you. That's the end of this presentation for today. As said, the topic was more or less humidity and not steam experiments. I just wanted to make sure that everyone understands that there's a difference. I hope everyone understood that there's a difference. So I have to say thank you from my side. Thank you for your attention.